This figure shows het Hollands Profiel, a cross-section profile for the Dutch provinces of Holland, which is a special case or example of steady groundwater flow in a leaky aquifer. The figure shows a Dutch polder made up of a leaky confining layer consisting of Holocene clay overlying a leaky aquifer with Pleistocene sand. Water is pumped from the polder and the hydraulic head or water table in the leaky confining layer is, to keep our feet dry, artificially maintained at the level HA in meter. In reality, this HA would lie slightly below the land surface, but here, simply for ease of calculation, HA has been set at the land surface. As the reference level, a hydraulic head of 0, we will use the top of the underlying impermeable base. The dike in the cross-section is simplified to an impermeable vertical screen above the leaky aquifer. Water from the river flows horizontally into the aquifer, and part of the water seeps upward through the confining layer, where again, to keep our feet dry, it is pumped off into the river again. Because of this, both the volume flux through the aquifer and the hydraulic head in the aquifer diminish from left to right. The hydraulic head in the aquifer is given by this dashed line and can be measured by lowering a piezometer tube through the confining layer into the aquifer and then having the piezometer screen within the aquifer. The difference in the hydraulic head of the aquifer and the artificially maintained constant hydraulic head HA in the polder therefore also diminishes from left to right. In this example of het Hollands Profiel, the right boundary condition is taken at infinity. At infinity, the horizontal groundwater flow through the aquifer has diminished to 0, and the difference in hydraulic head between the aquifer, the dashed line, and the polder, HA, has also diminished to 0, and thus the upward seepage through the confining layer also is 0. We call this setup of het Hollands Profiel an infinite polder. For both finite and infinite polders, a finite polder being a polder with a fixed boundary condition to the right, we will see an example of this slightly later on, the hydraulic head distribution with horizontal distance x in the aquifer, thus the potentiometric surface shown as a dashed line in this figure, can be determined from the water balance of this column, or rather rectangle of the subsurface, and then described by the following equation. H is the hydraulic head in the aquifer at location x in meter. HA is the artificially maintained hydraulic head in the confining semi-permeable layer in meter. E is the base of the natural logarithm, a mathematical constant approximately equal to 2.71828, etc. X is the distance from x is 0, and lambda is the leakage factor in meter, and lambda is the square root of Kd times C. Kd is the transmissivity of the aquifer, and C is the hydraulic resistance or vertical flow resistance in the overlying confining layer. C equals the thickness or depth of the homogeneously taken confining layer, small d, divided by the vertical hydraulic conductivity, small k, thus meters divided by meters per day giving days. So C is the resistance of the confining layer in days, and Kd describes the aquifer in square meter per day. Thus Kd times C is in square meter. Taking the root of this, we have the leakage factor in meters. The leakage factor is large when the aquifer has a high transmissivity and when the hydraulic resistance C of the confining layer is also large. Horizontal groundwater flow through the aquifer then dominates over the vertical seepage through the leaky confining layer, and as a consequence, in this Holland's profile, the hydraulic head in the aquifer, H, then diminishes relatively slowly with distance x from the left canal. Conversely, the leakage factor is small when the leaky aquifer has a low transmissivity, so a low Kd value, and when the hydraulic resistance C of the confining layer is small. Vertical seepage through the leaky confining layer then dominates over the horizontal groundwater flow through the aquifer, and then as a consequence in this Holland's profile, the hydraulic head in the aquifer then decreases relatively fast with distance x from the left canal. The main equations in determining the shape of the potentiometric surface of the aquifer are, as to be expected, the continuity or water balance equation and Darcy's law, the Darcy equation. These are combined for this column or rectangle. I will now only highlight the ingredients, so to speak, as some of these will be most useful when making hydrological calculations for leaky aquifers. This slide shows that column again. Here we have the aquifer with depth large or uppercase D, horizontal hydraulic conductivity large K, width W, and horizontal distance delta X. And here we have the confining semi-permeable layer with depth small or lowercase d, vertical hydraulic conductivity small k, and the artificially maintained hydraulic head HA is given here, is drawn in as a flat plane. And here below we have the confining layer again, but now turned on its side. The water balance for the aquifer part of this rectangle of the subsurface using units of square meter per day reads the volume flux Q in the x direction equals the volume flux Q out in the x direction plus the volume flux Q out in the z direction. The volume flux Q in the x direction square meter per day equals the volume flux density Qx in the x direction meter per day times the depth d perpendicular to the groundwater flow, the depth d of the aquifer. The volume flux Q out in the x direction also equals the volume flux density times the depth of the aquifer, but now with regards to the volume flux density of the groundwater flowing out of the rectangle. dqx dx is the rate in which qx changes with x. Merely as an example elucidating this principle, the slope in this small figure. By multiplying this rate of change, this slope, with the section delta x where the change takes place, we obtain the total change, dqx dx times delta x, over the section, as indicated along the vertical axis here. Q out in the x direction can then be represented by this equation. Darcy's law for the aquifer can simply be written as Q with a prime in the x direction equals minus the Kd of the aquifer times the hydraulic gradient. The hydraulic gradient is the slope of a tangent line touching the potentiometric surface, the earlier dashed line, at a chosen location x. In this Holland's profile, the hydraulic gradient diminishes to the right. For the vertical volume flux density in the confining layer, we can write Qz in meter per day equals minus K, the vertical hydraulic conductivity K, times the hydraulic gradient. The hydraulic gradient is the hydraulic head to which the water flows, thus HA, minus the hydraulic head from where the water flow dispatches, H of the aquifer, and this hydraulic head difference we must then divide by the location to which the water flows minus the location from where the water flow dispatches, thus the thickness or depth small d of the confining layer, d for upward flow being a positive number. And then, of course, the volume flux in the z direction equals the volume flux density in the z direction times delta x perpendicular to this vertical flow. Inserting all these equations in the above continuity or water balance equation and some smart mathematics delivers the hydraulic head distribution of the aquifer with horizontal distance x as this equation, with lambda being the square root of Kd times C. Again, the values of C1 and C2 can be found by inserting the boundary conditions. For a finite polder, as shown here, the boundary conditions, with both a fixed left boundary and fixed right boundary, are: when x is 0, h equals h0, and then h0 equals ha plus c1 e to the power 0 plus c2 e to the power 0. E to the power 0 is 1, so h0 equals ha plus c1 plus c2, and thus c1 plus c2 equals h0 minus ha. When x is L, then h is HL, and HL equals HA plus C1 e to the power L divided by lambda plus C2 e to the power minus L divided by lambda. So all of this then equals HL minus HA. We have now two equations with two unknowns, C1 and C2, and we can solve that mathematically. The general equation with these boundary conditions can also be used for a finite terraced field from where we have downward seepage through a confining layer into an aquifer and groundwater flowing horizontally out of the aquifer at the boundaries of x is 0 and x is L. In this cross-section figure, H0 and HL are 26 meter, L is equal to 500 meter, and HA equals 27 meter. For an infinite polder at Holland's profile, as shown here, the boundary conditions are: when x is 0, then h equals h0, and then h0 equals ha plus c1 e to the power 0 plus c2 e to the power 0. So h0 equals ha plus c1 plus c2. Thus c1 plus c2 equals h0 minus ha. When x is infinity, then h becomes HA, and then HA equals HA plus C1 e to the power infinity plus C2 e to the power minus infinity. Thus, C1 e to the power infinity plus C2 e to the power minus infinity equals HA minus HA, which is 0. So this term equals 0. Of course, e to the power minus infinity is 0, and e to the power infinity is infinity. And in order for this addition of terms to be 0, this term already is 0. C1 must be 0. So C1 is 0, and thus C2 equals H0 minus HA. We can insert C1 and C2, these values for C1 and C2, into the original equation. And then this is the equation we get. Thus an equation without this term in it.